Here's problem 3026. Two very long parallel wires carry currents in the positive x direction. One wire, current of 15 amps, is coincident with the x-axis. The other wire, current of 50 amps, passes through the point 0.4 millimeters 0. What is the magnitude of the magnetic field at the point 0.003 millimeters? So we want to find the magnetic field at a point on the z-axis when our currents are on the x-axis or in the xy plane. So let's turn our whole coordinate system 90 degrees so that the x-axis is actually going into the page. And then our z-axis would be to the right. So we're going to have a z-axis to the right, a y-axis that's going up, and an x-axis that's actually going into the page. So we're going to have one current that's going into the page along the x-axis, and then another current that's going into the page at y equal 4 millimeters. So this point that we're considering is at x equal to 3 millimeters, and hence it's going to be 5 millimeters away from this second wire. So we have I1 equal to 15 amps and I2 equal to 50 amps. Sounds good? Now as we're considering these currents, using the right-hand rule, there's going to be a magnetic field going clockwise around each of these currents going into the page. So if we were to consider the clockwise around wire number 1, it would be going around like this, and this magnetic field B1 would be going straight down in the negative y direction. And if we were considering clockwise around wire 2 at a radius of 5 millimeters, then B2 is going to be going down like this, perpendicular to this radius here, this 5 millimeter radius. Alright, sounds good. Let's find the magnitude of these two fields. They're both infinitely long wires, so B1 is going to be equal to mu naught I1 over 2 pi R1, and that's going to be 4 pi times 10 to the minus 7 for mu naught. I1 is 15 amps over 2 pi, so I can get this to right, times R1, which is 3 millimeters. The 4 pi divided by 2 pi is going to give us 2 left over there, and then the 15 divided by 3 is going to give us 5 left over there. So this is going to be equal to 10 times 10 to the minus 4, or we could say this whole thing will be 10 to the minus 3 Tesla in the negative y direction. That's B1. Magnetic field B2 has a magnitude mu naught I2 over 2 pi R2, and that's going to be equal to 4 pi times 10 to the minus 7 times 50 amps over 2 pi, and then we're 5 millimeters away from that wire. The 4 pi divided by 2 pi is going to leave us 2 here. The 50 divided by 5 is going to leave us 10 here. So this is going to be 20 times 10 to the minus 4, or 2 times 10 to the minus 3 Tesla. And it's going off at that angle, as we consider here, is going off at an angle like this. This is our B2. Let's call that angle alpha. So we're going to call this angle right here alpha. And actually, it's, if we consider this 3, 4, 5 triangle right here with the angle theta right here, the large angle 53.1 degrees, then theta's complementary angle, it actually will be alpha in that 3, 4, 5 triangle, right triangle. And this alpha is the same because this is also a right triangle as we go radially outward tangent on that circle. So this is alpha here, 36.9 degrees, and part of that 3, 4, 5 triangle. Sounds good. So if we were to write these two as vectors, B1 would be actually totally in the negative y direction, and they would be equal to a negative 10 to the minus 3 J Tesla. And B2 would have two components, one in the negative z direction, which would be a negative 2 times 10 to the minus 3 cosine alpha k minus 2 times 10 to the minus 3 sine alpha j Tesla. So for B2, this is going to be equal to a negative 2 times 10 to the minus 3 cosine alpha. As we look at that 3, 4, 5 triangle, cosine alpha is actually 3/5 k minus 2 times 10 to the minus 3, and then sine of alpha is 4/5 J Tesla. I'm sorry, the cosine of alpha is actually 4/5, and the sine of alpha is actually 3/5 as we look at that triangle. So this is going to be equal to a negative 1.2 J, 1.2 times 10 to the minus 3 J, minus 1.6 times 10 to the minus 3 K. So if we look at our total field, which is the sum of these two, that's going to be equal to a negative 2.2 times 10 to the minus 3 J minus 1.6 times 10 to the minus 3 K Tesla. The magnitude of this magnetic field is going to be the square of the components add together square root. So this is going to be a negative 2.2 squared plus a negative 1.6 squared, all that square root, times 10 to the minus 3 Tesla. And that's going to be 2.72 times 10 to the minus 3 Tesla. So that is the magnitude of our resultant field, 2.72 times 10 to the minus 3 Tesla at the point z equal to 3 millimeters.